Hello and welcome to the channel. My name is Shiki and today we're going to take a break from the Path to DevOps series that's ongoing on this channel, and we're actually going to circle back to our tutorial series, continuing with a deep dive in containerization. If this sounds fun, let's jump straight into it. Before we jump into our slide deck, I just want to mention that this is the second part of the containers course. This is the advanced part, and there's also a 101 or beginner container course on this channel that you can find and will be linked at the end of the video. So for in-depth stuff, this is it. For low-level stuff, beginner concepts, just getting you started with containers and understanding them, it's the other course. I recommend watching both, why not, but it's your choice. So without further ado, let's understand advanced concepts. The first concept that we're going to discuss is what are the Docker components we're actually using when we're running Docker commands on our machine, and then we'll go into the architecture of these Docker components. So there are two major constructs in this Docker architecture, and it's basically the client side and the server side. When we talk client side, we usually talk about the Docker CLI. When you run commands like Docker PS, Docker image list, and stuff like that, that's you running from your CLI, which stands for command line interface, and you're actually sending a request towards the Docker server to do something for you. Yeah, so you're the client. Also, other clients, you can see them here, are REST API calls, or if you're using a programming language to build a wrapper for Docker, then you might be using an SDK, a software development kit. That's what SDK stands for. And then on the right side of things, we have the server side. That's what receives your request from one of the clients and does the action for you, creates that container or pulls that image, renames that image, whatever you want it to do. And basically, the server side is composed of three big concepts. Runc, which is specialized in building images and starting and stopping containers, and containerd, which specializes in pulling images, managing networks, and managing these Docker objects. And then there's dockerd, which exposes the API that you're actually integrating with. So basically the client side of things talks to the API of dockerd, and it's actually dockerd that implements both of these, runc and containerd. So you can imagine them like a pyramid with dockerd on top, and behind it's runc or containerd. And this is going to get clearer as we move on through the slides, because here we have a architectural diagram, which will give you a lot more insight. So in the leftmost box, we have the Docker client, and initially, let's say we use the CLI, where we run the Docker image pull command. And when we run this command, the API from dockerd will receive the request, and it will actually try to get the image manifest initially from the local registry. This component, the dockerd, because it's a image pull command, it actually talks to the underlying structure called containerd, because that's its role. Containerd's role is to look at images and manage them and pull them. And it will initially check, as I said, if the image is in the local registry. For this example and for simplicity, it's not in the local registry. So it will go to the remote registry, because we asked for a specific image, so it knows the name of the repository of the registry where the image can be pulled from. It goes to that remote registry and it queries the image manifests. It finds the one we're looking for and it pulls it locally. And now we will have the image in our local registry. And then let's say from a different client, let's say an SDK, we're using whatever Python Docker SDK. We initialize this method of client containers run. So we're trying to run a container now from this image. The API is also the one that receives the request. And this time it's a post inside of containers create. And because it's a run container command, it's the runc's obligation or role to run the container for us. And it will go into the local registry, grab the image that's now there, and then it will instantiate a running container from that image. Now, I know this was quite complex, so take your time, review the whole diagram and try to understand the structure, the sequence of steps as you go from one to the other and what's happening behind the scenes, because it's quite important to know this when you're using Docker and to understand the architecture behind the scenes, what component does what operation for you when you request it. Next up on the list is the important subject of image layering, which I believe everyone should know as they study Docker, and they should understand it, which is why I'm trying to explain it best I can on this slide. I would like you to see that there are two arrows on the screen. The white one is descending, the bluish light blue one is ascending, and I would like to read the text next to them accordingly, because on the left side we're going to have a Docker file, and on the right side we're going to have the image with its layers as it's creating. So let's say in our Docker file the first clause is a from, so we're saying from Ubuntu latest, and in our future image that's the first layer, the foundation layer, which gets added. And as you see here, this layer and every layer will have a random ID, and we'll also have a size. In this case, the Ubuntu latest image has around 358 megs at the time of shooting. And then let's try to install the nginx server, right? So we're running run apt-get install nginx -y for confirmation, and it's going to create a secondary layer on top of the first layer. This one is a lot smaller and has a different ID. And then the last command is cmd systemctl start nginx to start the nginx server, and this will also create a layer for us. So this is basically our image. If you can notice, there's one layer for each of the keywords here in the Docker file, and these are the read-only layers of the image. Once you run the command docker build and you obtain an image from your Docker file, you can't actually edit that image, right? So if you want to make a change to the image, you need to first make a change in the Docker file and build again. But when you run the image as a container, a new layer gets added right on top, and this is the read-write layer. It's the one where you actually have access to change stuff, because as you probably know, if you enter a container with the docker exec command, you can install stuff in there and you can delete stuff or add files, make changes. Well, everything that you do will be marked here in the read-write layer, and if you delete this container, then the read-write layer will also get deleted, and you will only remain with the base image. So all of your changes will be lost. Yeah, so this is an ephemeral storage layer. As long as the container is running, the read-write layer is there containing the information. But if you delete the container, you lose the read-write layer. You are only left with the image, which you can reinstantiate again in or as another container. Time for a demo so that we can take that information we've seen on the slide and actually understand it. Now this is a basic Docker file, and you can find it on my GitHub account. It was also used in the initial Containers 101 basic concepts training. I will also link it in the description, so no worries, you can find it. And it's a simple Docker file. We just take a Ubuntu operating system image and we put some labels on it. We install curl, we also add a markdown, we install nginx, and we start nginx as the main process. Nothing complex, right? So let's build this image and see how those layers look, and then start it as a container and look inside of it, make some changes, you know, all the good stuff. So the first thing is to build a image from this Docker file, and the command is docker build dot for current directory minus tag, and let's say containers 102, yeah, because this is the second training we're doing on containers. And when I hit this command, you will see that everything just got created instantly, because I had already built from this Docker file previously. So the image was already here. I already had it locally. It just renamed it. And all of this text that you see here is basically reusing layers that I already have somewhere on my operating system. So step 1 out of 9, as you can see, is the first clause in the Docker file, yeah, from Ubuntu 20.04, and this is the first layer ID. And then you see the second one is label owner equals Shiki, yeah, there we have it, and it says here using cache. So this is an amazing Docker mechanism. It's basically telling us that once you've built a layer and you don't change anything, in the order of layers, it's basically stacking them like Jenga. Yeah. So the base image is this, and then it adds 7.6 on top of 2.0, and then it adds 1A6 on top of 7.6 on top of 2.0, and so on. So in the end, you'll get a tower of 9 layers, where the bottom is actually the first one in the Docker file, and the top is the last one. Now, the interesting part I want to show you one more time is, let's put here, after we copy the markdown, let's put a new one. Let's say label again, and say day equals today. I'm just saying, let's just put this in quotations as well. And now the interesting part is I will run the same exact Docker build, but notice what happens. So what's different? The first, I don't know how many were these, 7 layers? 6 actually. So the first 6 layers were created using cache. And then starting from the 7th layer where I made my change, I inserted my change, everything else needs to be built again inside of a different intermediate container and added on top. Yeah, because the order changed. I inserted a new layer in the middle. So now the Docker engine is actually running a run apt get update and apt-get install nginx one more time. And then all of the subsequent layers, because now we have 10 out of 10 instead of 9 out of 9. So this is very useful in case you want your Docker build to be fast and you're also trying to make changes to your Docker file, adding new functionality. Make sure static information comes first in the first layers, and that's going to be useful because you're never going to rebuild that. And then information that actually changes, I don't know, like installing packages of different versions, stuff like that, add those in the end, because those are going to be processed, but the first layers, once you build them, will remain in the cache of the Docker engine. And it's going to be able to say using cache. You can obviously use the explicit flag when you use Docker build and tell the Docker engine not to use cache. In case you're wondering if this is possible, it's totally possible, and it saves you from a lot of trouble when you have versions with the same name but different contents. For example, if it's your private repository that you're building from, you have a base image like my image latest, and then you update that image. The name is still my image latest, but it has a different content, and you're trying to build from it again. You might be using a previous version with the same name. And in this case, you want to make sure you always build without using cache. But in our case, it's not that important. So I just hope this made sense. The way Docker layers information in an image, and then also how Docker uses cache. And to finish this, I'm also going to run the image. Not here, obviously, in the terminal. So Docker run, and this is it. -d because we want it detached, and yeah, it's the syntax. Sorry for that, I'm lazy. Okay, so it returned the ID. my container is running, and I can basically docker exec inside of it, which means I will enter the container. And now I'm inside of the container, right? So as I said, let's do an ls, and you can see here the coolest markdown.md exists. Now what I want to do is remove it, and I'll actually create something different. I will echo hello there, new markdown.md. Yeah, and you can see here we have it. This is our new file, and I'm going to exit the container. As you can see, the container is running. Yeah, it's called Practical Newman. And now if I do a docker stop oh, sorry, the name was also taken. Yeah, now it's stopped. And if I do docker start and I exec again, we still have the markdown. Yeah, so the stop and start, just restarting the existing container, didn't remove the read-write layer. It just made it pause for a second, let's say. And now if I want to actually destroy the read-write layer, all I have to do is, I'm going to go with force because I had to stop the container and then remove it, but I'm just going to forcefully remove it. So now the container no longer exists. It has been deleted. And if I rerun it and I enter the new ID, if I enter the container one more time, you will see that the old markdown is here. Yeah, so the image was reinstantiated as a new container with everything it had inside of it. And in the old container, even though I've deleted the markdown and created a new one, which stated hello there, once I deleted that container, all of my changes on the image were lost because the read-write layer on top got deleted with the container. All right, next topic on the list is Docker volumes, and we've already discussed about how a container looks when you dissect it with the read-only layers and the read-write layer. Well, the read-write layer is ephemeral storage, which means you can store stuff inside of it, but if you delete the container, you lose the read-write layer. So what happens if you need to persist some data in one container or in multiple containers, no matter if they get stopped or deleted? What if you're trying to run a database like MySQL and you write stuff into that database? You wouldn't want, in case power goes down and you lose your container, your machine just restarts and it lost the container, to lose the data in the database. And that's where Docker volumes come into play, because they are a persistent storage solution. It's a way for you to persist data from the container onto the host. And it's quite simple. You have two things to a volume. It's the storage location. Yeah, you basically have a directory on the host, and in that host directory, that's where you put the data, let's say, and you mount that host directory as a path inside of the container. So when you are inside of the container and you're writing something in here in var lib mysql data, you're actually writing the data on the host in this path, in var lib docker blah 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 data. Okay, so it's basically not writing directly in the container, you're writing through the container directly on the host. Okay, so on to the volume demo. The first thing I would like to show you is that if you run docker volume list, you will see the list of volumes that you have. In my case, 0. So let's create one, docker volume create, and let's call it my volume. And it returned my volume string, which means it created my volume. Let's check that out. Yep, there we go. We now have a local driver type volume. Yeah. So what are we going to do with that? We're going to mount it to our image as we run it as a container. So docker run -d for detached. Let's give it a name. Let's say volume demo. And then this is the syntax. Source is going to be my volume, and target is where you mount it inside of the container. Let's say /volume, and the image is containers 102, and there we have it. So now if we enter this docker exec and we enter, I'm actually going to use the name now. Okay, and do an ls. There we go. We now have a new directory called volume. So let's interact with it and see how it feels. First things first, let's go inside of it. So I entered the volume directory, and let's say echo hello from the container inside of container greeting.text. All right, and now let's just open a new terminal. Yeah, this is still my volume. And let's inspect it. And it says here that the volume is mounted in var lib docker volumes, my volume, and underscore data. So this is going to be troublesome to find because I'm actually on a Windows machine, as you see. But let's search for it together. A few moments later. Okay, so this took way longer than I expected, but I was able to find the location. The volume actually exists on your machine, and in order to access it, you need to enter your Windows subsystem for Linux. And you can do that by //WSL and then $, and then another /. And here we see Rancher Desktop, and then we can go to the path var lib docker volumes. The name of the volume is my volume, and then inside of underscore data you will see that I have container underscore greeting.txt, and if I open it, it says hello from the container. So as you can see, I was able to write something from inside of the container. Yeah, in here I'm inside of the container. You can see this is the container ID right here. If you want, let me just give you one more in real time. Yeah, so bam, and let's open, refresh. There we go. We now have 2 text documents. Okay, but what happens if we want to do it the other way around? So let's write from the host a text document, and let's open it. Make it all caps. Yeah, we're angry at it. So now we have 3 files inside of the host, and if we do an ls, you see we also have 3 files inside of the container. And if we do an cat hello from the host, yeah, so it's a 2-way road. You can write from the container to the host and from the host to the container. Obviously you can manipulate that by having permissions. You can make it read write as it is right now. This is the default, or you can only make it read only, and that means you could read what's on the host from the container, but you couldn't write. You could only write from the host inside the container. Yeah, so if I would do a read only it would work for me to create a new file here, but if I wanted to create something from inside of the container, it wouldn't let me. And now let's test the most important part of a volume, which is durability, let's say. I'm going to exit the container, and I'm going to say docker remove minus force, and I need the name of my container because I don't really know it anymore. Yeah, volume demo, this is it. So this got deleted, but the volume still exists, right? So now I'm going to create a new container, and I will name it volume demo 2. It's going to be created from the same image, and it's going to mount the same volume. Yeah, and I even want to change the location where it's mounted. I don't know, let's say, yeah, /Jupiter, doesn't even matter. So now we do docker exec, we entered the container right now, volume demo 2. And if we do a change directory to /Jupiter and we list, we have all 3 files. Okay, so everything was persisted from the previous container into this one because we used the volume, and everything was actually persisted on the host at this location. The next topic on our agenda, Docker networks. Also constructs made to help containers work better, just like volumes were. So what's a network? And let me present you a diagram. It's basically the way in which, or the medium through which, 2 containers communicate with one another and maybe even with the host. Okay, everything that sits on the same network basically has the capacity or the possibility of communicating with something else on the same network. Types of Docker networks. The first one is the default bridge. As you've seen, when I run the docker run command, I'm not specifying any flag for network, which means my container is going to be dropped into the default bridge. All of the containers run by default inside of it. If you don't specify a network, this is where it goes. Okay, and this one does not support DNS resolution. Yeah, so you can only go IP to IP. A user-defined bridge is a custom network which supports DNS resolution. This makes it easier for containers to communicate between them because you just give them human-readable names, and then they can communicate with one another. If you are following the Path to DevOps course, in the Docker Compose file for running the 3 microservices locally, each of the services has a name. And that's possible because we're actually creating a custom network in the Docker Compose, and that's something implicit. I'm not specifically or explicitly saying I want a new network, but Docker Compose does that for you. So it creates a user-defined bridge, and it puts your containers inside of that user-defined bridge, and they can find each other using DNS resolution. Third type is the host network, where basically network isolation does not exist. Everything is running directly on the host. And then we also have none, which means no containers can communicate with other containers. Everything is isolated. Yeah, you only have the loopback interface on the container. Let us first see what networks we have available by default. And if I do a Docker network list, you will see that we have 4 networks, actually 1 of each type we've discussed so far. So we have the default bridge, we have the host, we have the none, yeah, so bridge driver, host driver, null. And then we also have a custom user-defined bridge. It's also a bridge type, but it's user-defined. As I said, for Path to DevOps, when you actually run the compose, it will create a network for you, and this is that network. But apart from these ones, let's create another one. Docker network create. And I don't know the syntax by heart, so I always use -h for help. And let's make this bigger. This is better. So it says here, create a network, and I want to create a bridge type network, a default bridge, and this is actually the default, so I can either specify it or not. But I will specify it. Yeah, so let's say that's what I wanted to do here, yeah. Driver bridge. And let's give it a name, my network. And here we have an ID in return, which in Docker terms, it means everything went right and I should have a new network. Let's check that out. And there we go. We have my network right here. So if I wanted to run a container inside of it, let's get the run command from earlier. And this time, instead of mounting the volume, let's just put this, let's change its name, network demo, and let's put it inside of a network. Network equals my network. And then there we go, everything is running. So sorry, Docker container list or PS or whatever you want to call it. So here we have network demo is here. And if we inspect my network, yeah, you can see here the container network demo appears as attached to this network. Now I'm not going to do a more complex demo. There's no need for us to actually put a lot of containers in the same network at the moment, because we're going to see that when we touch on Docker Compose a bit later on. Next up on the list, Docker Compose. And this is pretty simple. As you can see on the screen, it's a set of tools in YAML format which help people run multi-container applications easier. Instead of running each container from the command line, you define in a descriptive way in YAML format your desired outcome, and that gets created by the Docker engine. Let's see a demo so you guys understand what I'm talking about. Yeah. Okay, we're back to our favorite repository, the Path to DevOps Initial Setup repo. And in here you see we have the docker compose.yaml file, which you can also find on my GitHub account. Download it, play with it, whatever you want. So as you can see here, let's minimize everything. This is quite straightforward. You have two top level key value pairs, let's say. The first one is the version, which is 3, and then you have services, which is a list. And inside the services list, you have 3 services. You have product API, cart API, and frontend. Each of these services corresponding to an actual microservice, an actual container image that we plan on running. Product API has some environment variables declared. Very straightforward. Again, this is a list of environment variables. We declare the image, a restart policy, and port mapping, yeah, from host to container. Okay. Same thing for cart API, same environment variables, obviously different image because it's a different application, same restart policy, and slightly different ports. Okay, we can't map 2 identical ports on the host to the same container port. Yeah, so we have to change them. Product API will be running on 8080 and cart API will be running on 8081. And then we have the last microservice, which is frontend, and this one does not need environment variables to function. It just needs the 2 other to be started so that it can connect to them. And we have the image declaration here. We have the restart policy and also the port mapping. This time the frontend will be running on host port 9090. So this is a compose file. Yeah, it might look scary at first glance, but it's just a declaration of services I want to have created. And Docker PS will show us that no containers are running. And now I will do Docker compose up. You need to have a docker-compose.yaml file for this to work, but docker-compose up will do the trick. And I'm just going to stop this for a second and I'm going to try again. It says here it's trying to create first container, second container, 3 containers in total. Yeah, 1 for each service. And then this is the important stuff, attaching to the containers. Yeah, so it will also show us output from the container logs. So let's start this again and watch closely one more time. These are the logs from the 2 microservices. As you can see, product API is on green, cart API is blue, and the Spring Boot application initialized, both Spring Boot applications inside of the containers initialized. And they're trying to start right now. There we go. Yeah, started up in 18.63 seconds. So now if we start our browser, and let me just exit this and go to localhost 9090, you will see the front end. And all of this is working because behind the scenes in the Docker Compose file, we're creating 3 containers that sit on the same network so that they can communicate with one another. Yeah, and the front end is able to access the product API from where it gets this information. Yeah, the image and the product name, ID, and price. And also the cart API pops up this message whenever you click the buy now button. Simple website, not a lot of functionality here, but it's based on the 3 microservices. And by the way, if you're new here, there's the Path to DevOps series ongoing on the channel. Shameless plug, I know, but I'm teaching you guys how to apply DevOps principles on top of these 3 microservices. Yeah, so we're going to be deploying them to Kubernetes, playing with them, creating pipelines. So if this sounds fun, just join the channel, subscribe, and follow the content. Back to our idea. Yeah, everything is running in Docker Compose on the same network, and the 3 containers are communicating with one another inside of that network. Let's check that out as well. Docker network list, Docker network inspect, and we will check this bridge, and there we go. We have 3 containers inside of the network. Yeah, each of them has an IP address, as you can see, and a name. And they can find each other through DNS. The DNS label they can find each other through is actually the service name. Yeah, HTTP ://product API, HTTP ://cart API, and HTTP ://frontend in case you need that. And obviously the port, which is the container port. Yeah, and let me show you one more thing. The way frontend knows how to communicate with these 2 is through the configuration. Yeah, so as you can see here, it's going to product API, HTTP obviously, 8080, and cart API 8080. Okay, yeah, same here. So we've created a Docker network and we added the 3 containers inside of it. The front end knows how to communicate with the backends. The backends only need to know how to get to the database, and that's configured in the environment variables. Pretty simple. And the following step for learning more about containers is obviously container orchestration, where you will learn topics like replication, scaling, monitoring, a lot of advanced networking, and multi-node hosting, because so far you know how to spin up multi-container applications, make them run, make them all exist or coexist in the same network, maybe attach volumes to them, understand deeply what containers are, but still hardware can fail. So if you do all of this on only one machine, well, you might have a bad time if this fails. So that's why container orchestrators appeared, which are clusters of virtual machines, on top of which there's some software installed, and this software is designed specifically to scale containers to ensure that containers are running, that they are receiving traffic, that the containers are healthy, and if not, it tries to bring them up or notifies you of everything that's going not as planned.
I will be doing a deep dive on Kubernetes as well sometime in the future. I can give you a timeline. But yeah, that's container orchestration. It's going to be a topic and a training on its own. So if you find that interesting and if you want to take part in that, just leave a comment down below. And I will do my best to introduce Kubernetes to you guys in a bite-sized manner, trying to bring analogies, examples, and demos so that you can understand what we're talking about. I know it's been a lot of information and a lot of tough topics, so take a break, rewatch the parts where you want to clarify stuff, maybe drop a comment down below, and I'll do my best to reply to it. And from the bottom of my heart, thank you for taking the time to watch this tutorial from start almost up until the end.
Alright guys, that was it for today. I hope you enjoyed the information that I shared with you in the video, and if you have suggestions of topics that you would like me to cover or that you would like to see I talk about, then just put them down in the comments below. Thank you very much for your attention, and I wish you a great day. Say bye. Bye.